Hello there, and I hope you're having a great day today. Today's another great day to have a chemistry experience like no other. Learning about the effective nuclear charge. Love the effective nuclear charge. Yeah, it's going to seem like a weird thing, but when I first started learning chemistry, I had no idea what the effective nuclear charge was. Went through high school, went through college, still didn't know what the effective nuclear charge was. Got into high school, taught for 13 years. Didn't really know what the effective nuclear charge was. All of a sudden, I got a book that I started teaching out of, and it really went into the effective nuclear charge, and I was like, woo! It was amazing. And so I love teaching about the effective nuclear charge because it just kind of revolutionized everything for me. And I hope that you will enjoy learning about it, although I doubt you will love it as much as I do because I'm special. Okay, so let's see what we're talking about today. All right, electron configuration and periodic properties. Our objectives today to look at the atomic radius and electronegativity and look at the trends that we see on the periodic table for atomic radius and electronegativity. So your success as you walk out of here can be to define the atomic radius and electronegativity and to describe the trend within the periodic table for each of these properties. And you're like, yeah, but Powers, you just said we were going to talk about effective nuclear charge. We are, because effective nuclear charge is the underwriting principle behind all of these things that makes them all make sense. And that's why I'm going to teach it to you. All right, so let's talk about their atomic radius. The distance between two nuclei of bonded atoms, right? Half the distance between the nuclei of two atoms that are bonded together. Okay, that distance is your atomic radius. Okay, this one right here, sorry. Got that whole distance, half that distance is your atomic radius, yeah. All right, so as we look at a periodic table, we're going to see that this is going to decrease as we go across the period from left to right, okay, and it's going to increase as you go down. Now, why is it going to decrease as you go across the period? Well, because you're going to have a changing influence between the positive nucleus and the outside electrons, okay? And look, there it is right there. Effective nuclear charge, it's going to help explain this. We'll talk about that here in a second. And so the electrons basically are getting pulled in more closely because there's a bigger positive charge in the middle, and there's a smaller or a continual size of I just want to speak what's in my brain, and it just doesn't come out. I'm sorry, I'm trying. All right, so there is going to be an increased nuclear charge, whereas the shielding or core electrons, those are going to stay the same, and so it's going to have a bigger pull on the outside electrons. All right, so the atomic radius is going to increase as you go down a group. Why? Because you're adding more and more energy levels. Okay, we've learned about energy levels, and the more energy levels you add, 1s, 2s, 3s, 4s, it's going to get bigger and bigger, right? Okay, so here we are, effective nuclear charge. We're looking at a nucleus of a sodium atom here, okay? And we want you to think about the charge of the nucleus being the effective, or being the nuclear charge, right? And now we want to talk about its influence on those outside electrons, okay? So we're going to look at the shielding of the inner electrons to the outer electrons. Okay, so we are going to use the symbol ZEFF. Can't see that very easily, okay? The effective nuclear charge, ZEFF, is equal to the number of protons minus the core electrons. Okay, so if I ask you what's the effective nuclear charge, that's how you're going to calculate it. We're going to talk about what this means here on the next one, okay, the next lecture. So, okay, next slides. Okay, so as I go across the periodic table to the right, here I've got sodium. And notice how I've got 11 positives. Now let's look at my shielding electrons. How many electrons are in between the nucleus and the outermost electrons, the valence electrons? Hey, upstairs, will you settle down? Bouncing around up there too much, I tell you. All right, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I've got 10 electrons. Those are my 10 what I'm going to call core electrons. And so if I take 11 protons and 10 electrons, I'm going to have an effective nuclear charge of 1. Okay, I told you that it was ZeFF is equal to the Z minus the core electrons. So it's 1. If I look at magnesium, magnesium's got 12. How many core electrons? 1, 2, plus 8 is 10. Magnesium still has the same number of core electrons, but now it's got 2 electrons on the outside, 10 electrons on the inside, and so now my overall effective nuclear charge is a 2 plus. Let's look at aluminum. I've got 13 protons, right? Positive charge of 13 in the middle, settle down up there. And I've got 10 core electrons. My number of core electrons is the same. Okay, so if I have that same number of core electrons, now I'm going to have a 3 positive effective nuclear charge. So what's this like? To me, this is like a dance, all right? And you might have, let's say, 11 of a particular, attraction, particular gender on the inside. And let's say that I've got 11 girls on the inside. And these girls are all in a little huddle, and they're talking, and they're really excited to be at this dance, and they're looking to find some partners to dance with, right? Well, the people on the outside, these electrons, they're kind of like the guys that are also interested in dancing. But, there's always going to be some people that, other people are going to want to dance with a little bit more. And so what we want to see here is that what's happening is that these shielding electrons, these guys here, are going to have the first chance to pick and pair up with partners in the middle. Well, look at this poor guy out here, okay? This poor guy out here, he's got a little sad face on him because he is so far away. Although he wants to find a dancing partner, it's going to take him a while before everybody else has figured it all out, before he can finally figure out like who his dancing partner is, right? Now, there's 11 protons. 10 electrons are going to get a chance before he does. Okay, these guys are shielding. These inner core electrons are shielding this guy on the outside. He's not going to have as much of an attraction there because they're all going to have first dibs. It's kind of like that. Why? Because now look, the further we go, now these 10 get situated, but now there's 2 positive charges, 2 guys on the outside, and maybe they're not quite as sad-faced, maybe still a little bit sad-faced, okay? Because they've got now at least 2 girls that they can pair up with. As we go on, now these guys are maybe not quite so sad-faced, okay? They're kind of like meh. Maybe a little bit of meh there, because they are going to have 10 guys they're going to be choosing before they get a chance to choose. But then there's still going to be 3 girls, and so there's still going to be at least a little bit of choice there, where they're going to be like, yeah, hey, I like her better, and yeah, I like her better, and now blah, blah, blah. Well, the more you have those, that nucleus, okay, the bigger and bigger and bigger it gets, the outside electrons are going to be able to be attracted a little bit more because there's going to be more opportunities, right? All right, so it's kind of like a dance, although nothing at all like a dance, right? Because these are electrons. It's all about positive and negative forces being attracted to each other. And so what you have here in this case is you've got a greater positive with the same amount of negative, okay? So they don't balance out in the same way, okay? So there's more of an attraction between this positive and that outside 2 negatives. And there's even more of an attraction between this positive and those outside little bit of negatives, right? Why? Because there's not as many shielding electrons. There's not as much of that negative charge shielding the nucleus from them, shielding the positive charge for them. And that's what an effective nuclear charge is. And it will describe the size of the atom now, okay? The radius. We talked about the atomic radius, right? It's now going to describe why this is going to make smaller and smaller atoms as you go to the right, because there's not as much of an attraction between this 1 electron and a 1 plus, whereas 2 positive and 2 plus, 3 negative and 3 positive. Oh, wow, I'm so good. 2 negative and 2 positive in the middle, 2 positive in the middle, 2 negative on the outside, 3 negatives on the outside and 3 positive in the middle. the attraction is getting bigger and bigger, and so it's pulling those electrons into the protons more and more and more, okay? All right, so it's pretty cool, right? Effective nuclear charge. As the effective nuclear charge is increasing, you're going to end up getting more and more attraction. So this is actually going to make them smaller as you go to the right. We're going to talk about electronegativity in a little bit, and you're going to see how effective nuclear charge also affects that. All right, so there's very little change between the effective nuclear charge as you go down a period, right? Why? Because 3 minus 2 electrons is 1, right? So this is 1 plus. 11 minus 10 electrons is 1. So they have the same effective nuclear charge. If you're in a period, if you're in the same group or the same family, you're going to have the same effective nuclear charge, okay? So it doesn't really change. So the only thing that's really affecting it is how many energy levels you're adding. And of course, you are adding more energy levels, right? And so it's going to get bigger and bigger and bigger as you go down the periodic table. So here's an example so you can kind of see it. From lithium, okay, this is in the second period, all the way to fluorine, things get smaller, right? From sodium to chlorine, they're getting smaller, et cetera, et cetera, et cetera. Each row, you can see that they get smaller in each period because the effective nuclear charge is getting larger. The units, by the way, are nanometers. Okay, that's how the sizes are here, is in nanometers. Okay, so let's talk about electronegativity. Electronegativity is a measure of the ability of an atom in a compound to attract electrons. How much, and this is in a bound situation, okay? This is in a compound. These are not free atoms. These are actually two atoms that are already bound together. And we're usually talking about like a covalent bond where they're sharing, right? And so this is a covalent situation where they're sharing electrons. What is the ability of one atom to pull those electrons closer to itself? Okay, well, what's going to happen is it's going to increase across a period. You're going to end up getting greater and greater and greater ability to pull electrons closer to yourself as you go further to the right of the periodic table. And as you go down in a group, as you're looking down that family, it's going to decrease, or it might remain a little bit of about the same. And again, this has to do with the effective nuclear charge. Notice how it's changing as you go to left to right, and how as you go down, it doesn't change as much. The effective nuclear charge is about the same. And so, you know, in a group, and so it's not having a whole lot of extra attraction as you're going down. And in fact, it's going to get a little bit further away, and I'll talk to you about that here in a second. A little bit of a disturbing example, but we're going to cover it anyway. All right, so what you can see here is these values. Highest electronegativity, 4.0. Now, a scientist by the name of Linus Pauling, who's also responsible for you taking vitamin C, he's the one that came up with this concept. And he basically looked at a whole bunch of atoms and how they're interacting and seeing how much of an attraction they had to each other as they were pulling on these shared electrons. And so this whole table was basically done experimentally. And he started with the biggest, strongest attraction, fluorine, and he gave it a value of 4. And then the other ones just got values based upon what was happening with their experimentation. And so notice how hydrogen is a little bit more like what all these noble gases are, right? Because hydrogen wants one more to become satisfied, just like fluorine wants one more and chlorine wants one more. So hydrogen is actually, in some ways, belonging over here in an example. But for the most part, as you can see, it's going to increase. My attraction is going to get bigger as I go from left to right across the periodic table. And again, we're going to talk about that with regard to, actually, I'm going to go back to that one. We'll talk about that with regard to the distances that we have. So for instance, let's look at sodium and chlorine. All right, so sodium with that plus 11 in the middle, and we have chlorine. Actually, we'll look at fluorine because it's just a little easier to draw. Fluorine, and that's got a plus 9 in the middle, okay? But remember that these have very different effective nuclear charges because this has those core electrons, right? And it has that one extra electron on the outside. You know, this is really not a great example since I'm actually supposed to be talking about covalent bonds, and this is not a covalent bond. And then here with fluorine, we've got the 2 electrons in the inside, and then we've got 7 electrons on the outside. Okay, so this one only has 2 core electrons. My effective nuclear charge here is a +7. My effective nuclear charge here is a +1. Okay, this has a much greater effective nuclear charge. There's 7 extra electrons. 1, 2, 3, 4, 5, 6, 7. There's 7 electrons that are all scrambling. They all get a good little choice for who their dance partners are, right? And here's just that one. And then we've got all, just all those people that kind of get in the way. We already talked about all that, right? Gotta get all those in there. Okay, so what's the difference between how these things are going to be attracted? Well, this has got a lot of attraction. That positive, that's the effective positive charge of the nucleus. That's a big positive charge, right? And so as I think about, how that's going to bond with something, then that's going to really pull on things. It's going to pull electrons toward themselves, right? So let's assume that we're talking about hydrogen. What's it going to do to pull hydrogen toward itself? Woo! It's going to be a really strong pull compared to hydrogen on this guy, right? This is only a +1. That's only a +1. The pull of fluorine to hydrogen is going to be much stronger than the pull of sodium to hydrogen, okay? And so if they're in a sharing relationship and they're sharing those little electrons in between them, fluorine is going to pull that electron of hydrogen way harder and much more closer toward itself than sodium is. Sodium's like, yeah, I don't really want you. In fact, doesn't really want it at all. We wouldn't really see this bonding happen very much unless we kind of forced it to. But, if I were to compare fluorine with hydrogen, and let's talk about like astatine. All right, so astatine, and you've got all of these electrons. You've got more and more and more, like further and further and further out. Now, astatine might have a +7 nuclear charge still, just like fluorine. But these electrons on the far, far, far outside, there's a lot of shielding electrons. There's a lot of positive in the inside, but they're so much further away. That nucleus now, which has a +7 effective nuclear charge, right? Astatine normally has 85 protons, right? So this is a big charge in the middle, but its effective nuclear charge is the same as fluorine. And so hydrogen's little electron isn't going to be as attracted to the +85 because it's so much further away. It's going to be more attracted to the fluorine, which is +9, because it's so much closer, all right? So again, they have the same net positive charge, but because fluorine has its nucleus much more in a closer vicinity, it's going to be working. So if we're going to go back to the dance analogy, okay? If this is another guy that's like, hey, I can see that girl, and let's go ahead. I mean, like, she's only 10 steps away. I'm going to go dance with her, right? And this guy's like, whoa, she's on the other side of the gym. Yeah, okay, have a good night. Right? Like, it's too much work. I can't go all the way across the gym to dance with her. That's kind of the idea. The attraction isn't going to be there. Like, oh, I don't have good eyes. I don't know. Is she available? Does she have 2 legs? 1 leg? I can't tell. Can she even dance? I don't know. That's the idea here, okay? Effective nuclear charge and electronegativity. All right, so let's see if you can practice it. This is your turn, so this is where you're going to pause and practice. Ready? And we're back. All right, so which element has the large atomic radius? Would it be sulfur or silicon? Okay, so sulfur is number 16, and silicon is number 14, right? And so which one is further to the right of the periodic table? It's going to be sulfur. So sulfur is going to have the bigger effective nuclear charge, which means that it's going to be pulling things closer into itself, right? Because it's got a bigger attraction. So sulfur is going to have a smaller radius than silicon. Correct answer here is going to be silicon, okay? Now, sulfur or tellurium. Tellurium is below sulfur, same family, but it's going to be below. And because I'm adding extra energy levels, then I'm going to be adding more distance. And so that one's going to be tellurium. Which element has the higher electronegativity? Is it sodium or chlorine? Well, chlorine, again, it's going to increase as you go to the right. Chlorine is going to have a higher electronegativity because it has a higher effective nuclear charge, so it's going to pull electrons toward its center more. And then selenium or oxygen, again, selenium is below oxygen, and so the further you go down, the less attraction because there's a greater distance, so the higher electronegativity is going to be oxygen. Okay? Did you get them right? I hope so. Let's go on to the next one. All right, let's look at kind of some trends for our atomic radii. As we go across the periodic table, okay, so this is like lithium, sodium, this is all group 1 or family 1. As you go across, you'll notice that the atomic radii gets smaller pretty drastically in the beginning, and then it kind of flattens out, kind of levels out a little bit as you go to the end. It's still getting smaller, but it's not that big drop that you had at the beginning, okay? And again, as you go down the group, why is it getting bigger? Because you're adding those energy levels, adding principal energy levels. So your atomic radius is going to be getting bigger and bigger as it gets further from the nucleus. Here's the electronegativity with regard to the different groups. Notice how it starts with low electronegativity. And as you go across, this is from lithium to fluorine. As you go across, the electronegativity increases. Again, so these are your group 1 elements. And you can see that the electronegativity goes up. Now you'll notice some interesting things that are happening here. This is when you get into the D sublevel. You can see some ups and downs that are taking place here. And that has to do with the number of, the D orbitals that are filled, whether or not it's satisfied or not satisfied, if it finds a stable point or not. And so the electronegativity might change and the size can change a little bit too. Okay? But those are all individual ideas, but the trend is generally up. Okay, let's talk about ionization because there's something called ionization energy, which we're going to talk about briefly now. And the ionization energy has to do with what's going to happen in the size of the ion too. So it has to do with what happens when I lose an electron. In this case, I can see that my shell just got smaller, right? So if this is lithium, and I've got, my first energy level, it's got 2 electrons, and it's the second energy level, and it's got 1 electron. As soon as I lose an electron, I lose a whole energy level, right? So it gets a lot smaller. And so when you lose an electron, and you're on the left side of the periodic table, you're going to see that thing is going to decrease, okay? So ionization size, the ionization radius is going to be smaller when you have an electron lost and you're on the left side of the periodic table. When you just have 1 electron and you're going to lose a whole shell, that's going to make you quite a bit smaller, okay? So that's going to happen when you have a whole energy level, basically, that you lose when you lose an electron there, okay? So let's talk about this ionization energy. This is basically the energy change when an atom loses an electron. And notice, again, what we have here is an increase from our, first group elements, our family number 1 or group number 1. And as you go across to group 18, then they're going to rise. They're getting bigger and bigger ionization energy. Well, why? Well, because the effective nuclear charge, of course. As that effective nuclear charge gets bigger and there's more of a positive charge, it's going to be harder to rip the electrons off, okay? But as you go down a period, it's going to be easier. Okay, so down a family. All right, so ionization energy. As you go down a group, it's going to slightly do what? So here I'm going lithium, sodium, potassium, rubidium, cesium, francium. Okay, they're getting smaller, right? It's decreasing. You can see that same thing. Helium, neon, argon, it's getting smaller as you go down a group. And as you go across the period, it's going to increase, right? So it increases as you go across the period, and it decreases as you move down the group. Okay? And again, let's talk about that in terms of an electron. Here's just the main block elements. You can see that, again, it's going, as you go down the period, it's going to get less. And as you go across, I keep mixing up those silly words. Down a group, it gets less. As you go across the period, it's going to increase. I don't normally mix up my words like this much. So let's talk about the difference between, let's go back to fluorine and astatine, okay? So we talked about fluorine, and we're just going to show fluorine as something a little bit smaller like that. And then let's talk about astatine again. And astatine is in group 6, so it's got, you know, 6 different energy levels. And I want to talk about ionization energy. How much easier is it going to be to rip an electron off of astatine than it is off of fluorine? Well, the morbid example that I use on this, and I apologize, but it's a good one, is, you know, imagine that fluorine, the nucleus here, is where our parents are hanging out, okay? So our parents, 1, 2, 3, 4, 5, 6, 7. I've got my parents, and I've got my 2 littlest ones. They're just hanging out on the bench with me, and then I've got my 7 other kids that are hanging out. These kids are at the slide. These kids are at the swing set. Those kids are, you know, at the teeter-totter. And so I've got my 7 other kids here, and I've got a good close eye on them. I'm right there. I've got my eye on all of them, right? Nobody's coming in and swooping those kids that way. However, okay, what if we, you know, blah, 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 blah. There's so many little electrons all around here, right? I've got so many kids. How many kids do I have? 85 kids, all right? 85 kids. Ah, yeah, holy cow. A lot of kids. All right, it's been crazy. And so now I can still keep an eye on my first couple kids, you know, that are at the swing set and around the bench. But then these kids are, you know, off in the field a little bit closer. These kids are off playing soccer. These kids are out in the creek, and I can't even see them anymore. Those kids, you know, went downtown and they're doing drugs. I don't know. But they're so far away, okay? I have no way to keep track of those guys. How much easier is it for a stranger to come by and be like, "Want some candy, kid?" And I can't do anything because those kids are so far away compared to right here, right? That's the idea behind ionization energy. There's a strong attraction to, and I know, I'm sorry, it's a horrible example, but it's also effective. You're going to remember now. Those kids that are close, all right? Strong attraction because I'm really close to the nucleus, okay? Stay close to the family, to the parents, you got protection. The further and further and further out, the less protection you have. And that's because there's just so much that's there, and there's very little attraction to the outside kids, okay? So anyway, weird, I know. But like I said, you got to remember it now because it's so crazy and weird and morbid. All right, let's look at our next one. So now we have this concept called electron affinity, which is slightly different than electronegativity, okay? Slight difference between electronegativity and electron affinity. Electron affinity is the energy change when an atom gains an electron. Remember, before we were talking in electronegativity, we were talking about a shared bond, a covalent bond relationship where the nuclei of 2 different atoms are pulling and tugging on the shared electrons. In this case, this is not about that. This is about what happens when I gain an electron. If I can force you to have an electron, what kind of energy change do you have? Well, for the most part, most neutral atoms are going to release energy. Why? Because they get to a more stable state. Okay, so if I'm fluorine, I want an extra electron. It's going to help me get my full octet, my full valence shell of 8 electrons. And so when I can get that extra electron, I go and I actually get a little bit smaller even, and I actually have a more stable state, okay? A higher stability with lower potential energy. And so that's going to be a high electron affinity. Fluorine, you'll notice, is really high. Halogens are high in electron affinity. However, if I'm over here and I'm, you know, hydrogen, do I really want an electron? Okay, it's going to make me a little more stable, but not much, right? And so I'm not going to give off much energy when it actually happens. And some of these that are grayed out, you can see that the ones that are grayed out, they don't want an extra electron at all. These guys, noble gases, they don't want an extra electron. They're completely satisfied. And so if I were to give them an extra electron, it would actually take energy to put an electron in there instead of giving me energy when I, you know, let one absorb it. And so that's what electron affinity is. It's about the energy change when it gains an electron. The fluorine and the halogens, these guys over here, they're going to want those extra electrons. It makes them more stable. But some of these guys, they are not going to be more stable when they get an extra electron. Okay. Wow, you guys are like jumping up and down upstairs. All right, so yeah, I think that's kind of the idea. Fluorine is going to release a lot of energy upon the addition of electron. Noble gases don't. Oh, so blank as you move down a group. So electron affinity. I don't know what line to write on. It's bouncing around so much. As I move down a group, my electron affinity is going to decrease a little bit. Why? Because of the effective nuclear charge. I'm going further and further and further away. So these guys aren't going to want an electron as much as these guys. You know, I've got 85 kids. Do I want 86? Not really. If I've got 7, do I want 8? Sure. All right, so this is going to be decreases. And then, it's going to, as you go across the period, you notice how it's increasing as we go across the period. Okay. All right. So I think we are to the end. So let's check our objectives. What did we learn today? Can we describe what's meant by atomic radius and electronegativity and identify the periodic trends? Yeah. So we know atomic radius. We know electronegativity, shared electron pulling. We also know a couple other things. We learned about ionization energy. We learned about the ionic radius a little bit. We learned about electron affinity. We learned a few extra things even beyond that, but those are good things to know. And so, can we define atomic radius and electronegativity? Yeah. Can we describe the trend within the periodic table for each of these? Yeah. So atomic radius is going to get smaller as you go across. Electronegativity is going to go bigger as you go across. Atomic radius is going to go bigger as you go down. Electronegativity is going to get smaller as you go down. So they're kind of opposite trends, right? Okay, I think that's it for today. Thank you for listening and learning about, especially about effective nuclear charge, because again, that particular concept revolutionized how I understood so much of all of these different types of trends. And I hope that you can enjoy it as well, even if you don't appreciate it quite as much as I did. All right, guys, you have an awesome day, and thank you for listening and putting up with me and my blah, blah, blah. God bless you.